We will continue to explore the thermal reaction norm of development. We have seen previously the basics, and now we will discuss more about how we can estimate the parameters. So, in the previous video, we have described that we can use two different metrics to model the development of a turtle in field and considering the variation of temperatures. We can use SCL size, straight carapace length size, with a Gompertz model of growth. Here I recall the equation of the Gompertz model, but what is more interesting is what the parameter can tell us about the growth of the turtles. So we have three parameters in this model. K is asymptote. The unit is in millimeter if you use millimeter for the straight carapace length unit. Y0 is the equivalent size at laying. The unit is also in millimeter. And A is the growth rate. The unit is in time power minus 1. Turtles lay eggs at the gastrula or early neurula stage of embryological development, but here Y0 must use an equivalent size of the SCL. The size of a gastrula is not the correct proxy for Y0. K is the asymptote of the Gompertz model, but it is not the hatching size. We will see a little bit later how hatching size is related to K value. If we use a progression of development with a linear model of growth, the model is simply y equal AT, and A has no unit because we model a progression of growth from 0 to 1, but it has not real biological meaning. A is the growth of embryo. We saw this in previous slides that A must be estimated using a function, and we will not discuss this. Go to the previous video if you don't understand what's happened here. Now let's describe more precisely how we will fit the Gompertz growth model, what kind of parameters we need. The basic idea is to fit the values of the parameter of the growth rate that we saw just previously, so 4 parameters. So the value of these parameters that permit to predict the best the straight carapace length of hatchlings at the end of development. The straight carapace length of hatchlings is a measure obtained from field with mean and standard deviation to measure the heterogeneity of the size of hatchlings. It is possible to use a different value for each monitor nest, or a global value for all the monitor nests, or even a value obtained for the entire RMU. The value K of the Gompertz cannot be fitted with the data we have using field temperature, because there is a trivial solution that will perfectly work. This is A equal plus infinite, and then K equal M will be the best solution. So K value cannot be determined by this data. So the Y0 value also cannot be fitted, because again there is a trivial solution with A equals 0 and Y0 equal M. So again Y0 cannot be fitted with this value. To estimate K and Y0, we must go into developmental table. Here I copy an example of a developmental table for Hemys orbicularis embryo, and you see two columns that are the columns that will be interested for us. carapace length and age at 25 degrees Celsius or 30 degrees Celsius. K and Y0 must be obtained independently from developmental table. Then, if you plot the incubation days against straight carapace length, you see that you have a relationship, but the relationship is clearly not linear. This is normal because we won't use Gompertz model. If it was linear, it was simpler. Here we will use Gompertz model, and to estimate the Y0 value, the equivalent size at laying time, we must search what is the expected equivalent straight carapace length at time 0. You see that if you make just extrapolation, linear extrapolation from this point here, you will estimate negative straight carapace length at laying times. This is not correct. This is expected because you will see that Gompertz curve will look like more like this. Similarly, if you want to estimate the K value, the asymptote of the model, you see that here clearly it's slowed down, but at the end of incubation at 25 degrees Celsius and 30 degrees Celsius, you have not reached the asymptote. The asymptote is somewhere here. So the K value of the Gompertz model must be seen as a parameter that permits to slow down the progression of the Gompertz curve, but this is not the size of hatchling. To estimate this value, we must do application of Gompertz model in developmental table data. The idea is to fit this data using a Gompertz equation with A, the growth rate of the Gompertz model, dependent on incubation temperature, but with constant K and Y0. This fit is not straightforward. You cannot use the typical tools for fitting a Gompertz model because here you have uncertainty on both Y, the size, but also the time. So we must use a bivariate likelihood, and you can find the code in the description of this video. Let's do. Here I fit the data of the developmental table of Emys orbicularis using a bivariate Gaussian distribution. We can see that the fit is relatively good, and we can estimate the value Y0 and K for this data. The value of K by itself is dependent on the size of hatchlings. Then it is more interesting to use RK, which is the standardized value of K based on the size of embryos. And similarly, we can estimate RY0, which is the standardized value of Y0 by the size of hatchlings. This is simply a division. Let's do the same with Caretta turtles, data from Casca, the thesis of Jakub. And so we fit the same model using also bivariate Gaussian distribution, and we fit this data. If you look at this data and the previous one, you can move the cursor of the video to check how they look. Clearly the K value are very different. This is normal because the K value are proportional to the size of hatchlings, and hatchlings of Hemi's orbicularis is much smaller than the hatchlings of Caretta caretta. That's why the RK, the value of K divided by the size of hatchlings, are better description and could be species-independent parameter. On the other hand, you see that the Y0 value are very similar in both species. And here, this is the R Y0, which are different. So the Y0, which is the equivalent size at laying time, could be similar whatever the final size of hatchlings. Using these two examples, we see that RK and Y0 are very close to each other for these two species. It is not known at this stage if it can be generalized for all turtles. This is a work that we should do. Now, if we fit the progress growth model using the linear model, the basic idea in this version is to search for the value of the parameter of the growth rate of embryo that permit to predict the end of development being 1. The difficulty here comes from the 1 value. It is clear that the objective is to reach the 1 value, but what is the uncertainty for this objective? We must know an uncertainty to estimate likelihood and then use Bayesian statistics. The solution I choose here and in several previous papers is to use the standardization of the hatchling size and its standard deviation as objective criteria for the fit. The SSCL of hatchlings is a measure obtained from field with average, M, and standard deviation, S. Then we will search for the parameters that permit to predict an end of incubation at M divided by M equal 1, perfect, and standard deviation S divided by M. This is clearly a strong hypothesis, but I don't see other solution now. In conclusion, we have shown how to model the development of a turtle in the field, considering the variation of temperatures. We use two metrics, SCL size with a compared model of growth, or progression of development with a linear model of growth. Each of these metrics has force and weakness. When SCL size is used, a model of growth must be implemented with some parameters obtained from developmental tables. When the progress of development is used, the uncertainty of the criteria used as objective for fit is not known, and this is one weakness of this method. In the next video, we will continue to use this pattern of growth to describe how we can estimate the thermosensitive period of development for sex determination. Thanks.